Our next speaker is Dr. Wei and Mauricio. Dr. Wei is the Chief Technology Officer in Simtech and a Research Associate in Hillbred Department of Petroleum and Geosystem Engineering at UT Austin. His research interest focus is EDFM-related technology. He co-authored and co-authored more than 200 papers, and he's graduated from UT Austin as well. Actually, Dr. Wei is one of the core inventors of our EDFM technology. He hands-on EDFM applications and collect all kinds of solutions for fracture simulation with EDFM. And Mauricio Fiolas is a regional manager and the software advisor at Simtech. He is charging EDFM application in reservoir engineering and simulation, participated in multiple characterization projects from the projects all over the world. And his interest is about the integrated part from modeling to simulation with EDFM technology. So let's move on to this section, and let's welcome Dr. Wei. He's with me together in our College Station office, please.
Okay. Hi everyone, welcome to our EDFM workshop. This is a really exciting day for EDFM. So I'm happy to represent our team to give this talk. I will discuss about our EDFM applications for fractured reservoirs and some new EDFM development feature. This is the overview of today's talk. First, I will briefly talk about fractured reservoir simulation challenges. And then we'll move on our key embedded discrete fracture model EDFM technology. And then I will show some applications and our future plan for the new EDFM development. And finally, it's a summary. As we know, natural fractures and WAGs are really important for the conventional development, and also for unconventional development, especially hydraulic fractures, and also for the recent hot topic like geothermal development. However, there are some challenges for the fractured reservoir simulation. For example, fracture aperture is really small. They have small pore volume, and more importantly, there is a huge complexity in the fracture 3D orientation and 3D geometry. So how to accurately and efficiently simulate 3D natural fracture, that's a very big topic. In general, we often use a dual porosity, dual permeability model to handle that. That's only the choice now. But for us, we want to there is any better solution to model this 3D DFN. So that's key, the topic of today. We will discuss about our choice, like EDFM technology. So with our EDFM, you can easily and efficiently model and simulate any 3D natural fracture complexity, as shown in this figure. And also, we apply several US patents for this EDFM. These only show the one patent. Actually, we work on this EDFM technology more than about 10 years. In order to model production from 3D natural fractures like this figure, I compared three different methods with our EDFM. The first is like a dual porosity model. Second, like local grid refinement. Third one is the unstructured grid. However, you can look at the accuracy, flexibility, grading, and computational efficiency. Our EDFM performs the best. So we can use a simple structure grid to model production with any 3D fractures. So that's a very big breakthrough for the fracture reservoir simulation area. What EDFM does, and here I want to show the key concept of EDFM. Actually, we have two different domains. First is like a physical domain. Second is a computational domain. And in the physical domain, you can see we can easily embed a 3D fracture in the simple structure grid matrix. And we do not need an unstructured grid and local refinement. And then in the computational domain, we will have two different type of grids. First is the matrix, and second is the fractures. And you can see we have a 4 fracture grid to represent these 2 3D fracture. And after that, we will identify the non-neighbor connections between matrix grid and fracture grid. And finally, we will calculate the heat and flow transmissibility based on these 2 equations, because we also want to model temperature behavior. Here, we propose 3 different types of non-neighbor connections. First is like a matrix 2 fracture. Second is the fracture connection in the single fracture plane. And third is the fracture intersection between different fracture in the single grid block. And then we can calculate their transmissibility as shown in this equation. And you can see the transmissibility calculation only depends on the 2 grid distance, area, and permeability. It's not related with the oil and gas like fluid property, because all these properties go to the mobility here. So it works with not only blank oil model and also computational model. And all the equation here, we can calculate the transmissibility. So it's very different from a dual porosity model with a simple calculation of the shape factor. Now I want to talk about the key history, several milestone points of EDFM. The initial idea was proposed by Hearn in 1997 at UT Austin, and then Shell people applied the idea to model fault using different domain and special connections. And then in 2008, Chevron people did a great job to extend this idea to model only 2D natural fracture by Lee and Lee, but they use only 2D analytical solution for the transmissibility calculation. Then 10 years ago, in our group, Professor Stephen Nouri, we creatively proposed 3D EDFM because we really want to model only a 3D fracture, not only 2D fracture, right? Then we proposed all the type of non-neighbor connection, fracture well connection. We implemented this technology in our all in-house reservoir simulators like UDCOM, UTCAM, and also like corner point on structure grid. And more importantly, like Sergio and Hugh, we extend EDFM for the commercial reservoir simulator to use as a plug-in. And then in 2017, our SimTech to do commercialization of EDFM technology to speed up this EDFM simulation time and also make it more user-friendly, try to handle more challenging industry scale field studies. Then with our EDFM technology, you can easily couple any third-party fracture simulator and a reservoir simulator like a bridge. And then if you work on natural fracture simulator like Petrel, Fracman, FracFlow, we can easily and smoothly transfer all this fracture complexity into any reservoir simulator. Now, all these reservoir simulator with our EDFM, they can handle this 3D fracture easily. If without our EDFM, they cannot do that. So that reason I want to say our EDFM technology actually is a game changer for fracture modeling and simulation in our petroleum industry. Many people want to know what's different between EDFM and the dual porosity model. Here, I show a very simple model, try to help understand this question. In this case, you can see we have a 2 well, 1 injector, 1 producer. We have several natural fractures there, but you can see the natural fractures are not connected well, right? Then we set up 2 models, dual porosity model and the EDFM model. And you can see when you do water injection, the dual porosity model will have a very early water breakthrough. And what's the reason for that? Because from the pressure distribution, we can see we use the DPDK model, it overestimate the fracture connection. Actually, they are not connected. But our EDFM can capture non-connected fracture very well. I did figure show the water saturation change due from the injector and producer. You can see the water is difficult to transport to the producer. Actually, with our effort, we have a lot of field application in the world. Now we have more than about 12 different countries with many cases, and also we got a JPT journal and give 3 different reports as an emergent EDFM technology in our petroleum. Next, I will show some field applications using our EDFM. The first application is the carbonate reservoir. We propose a new DFN modeling workflow. Traditionally, based on like core data analysis, image log, outcrop, seismic, then we can propose like a conceptual DFN model. Then we generate the 3D DFN geometry. But for the reservoir simulation, we don't have a choice. We must use the dual porosity model to match your production to prediction. So we really think it's very challenging to accurately calibrate the fracture using the DPDK model. So that reason we can use our new EDFM to have a new workflow to model every single fracture. We don't do approximation like a DPDK model. And then we can accurately honor the geology model, and we can handle every single fracture without upscaling. Then we can do a better job to calibration of our fracture size, like length, height, aperture, permeability, with the fast history matching. This is a slide that shows the one project we did for the DFN modeling. Actually, you can see we have like image log, like core data analysis. We built a single well model to generate the DFN cross-wellbore. Actually, the size is uncertainty, but we know the number cross-wellbore. And then we do like analysis and prediction of the fracture distribution based on geological driver analysis. And then we can generate the 3D natural fracture density and the geometry. Then we want to use our EDFM to handle the challenges like how to calibrate your DFN, how to do accurate fracture simulation, especially for some carbonate reservoir. There is a challenging issue like water intrusion, how to model that. Then we can all handle that. Because we treat DFN, we treat the DFN every single fracture, not like DPDK method. We develop some special algorithm or software to handle some specific stuff like DFN connectivity. Here we develop a collision algorithm to identify fracture connected in 3D space, not only 2D. And then we can apply this connectivity algorithm to do like a real field test. This is show the more than 3 million natural fractures. Based on our software, we can identify like 10 different groups of connected DFN. So that's really important for the well design. So we want to drill some new well in the natural fracture area with a strong connectivity. And then you can see we also have another feature. We can tell you how many fractures in each group. And here you can see the biggest group, like light blue color for the main layer, including more than 26,000 natural fracture. Another key feature we developed is like we can change the fracture size, because the characterization of natural fracture size, this is the word Chinese topic. It's very difficult. Maybe we can do better job for the density, but the size is very difficult. So that reason we do the scaling of the natural fracture. You can increase your fracture size, especially for the cross-wellbore fracture, because based on image log, we know the location, we know the number, but we don't know the size. So we need to change the size to do like a production match. Actually, it's really sensitive. We did a lot of projects to use this feature. This shows the one case study. We can treat different DFN in different groups. For example, this is based on image log, like cross-wellbore DFN. And then we have some nearby wellbore DFN. We have some far away wellbore DFN. For different group of DFN, we can assign different properties. We did a lot of sensitivity study for the cross-wellbore DFN size, and then we can play with that, and then we can get a quick match. So that's really useful using DFN scaling factor. And also, we developed some shortest path modeling algorithm, because this is really important for the water intrusion in the carbonate reservoir. And we can identify from the wellbore and endpoints to the water layer, we can identify like a single shortest path, or you give like some region, we give like multiple shortest paths. Then we can treat this shortest path with different fracture like conductivity that you can better match for your water intrusion. We did several field case studies here, only show this one is a carbonate gas reservoir, and you can see this is a wellbore. We have 3 shortest paths. The other is the natural fracture. We can quickly play this shortest path conductivity. We can match your water intrusion, and we can show the visualization of water intrusion along this complex 3D natural fracture network. And then we can extend to the whole field fracture reservoir simulation. Because the whole field have made that is about 3 million natural fracture. So we do like different scale of fracture. For the small fracture, we upscale to single porosity model. And then we call big fracture as some big fault. We use EDFM to model that. And after that, we can do a quick match. After EDFM simulation, we can do much better visualization. And you can see here, we can visualize like water saturation and pressure along this 3D complex fracture network. And also we can visualize there in the matrix. So that's very useful to understand the fracture effect. This is another application for the water intrusion in a carbonate gas condensate reservoir. And they did a very good job for natural fracture characterization, but they need to match with water intrusion. Then use the same idea, we can do a quick match for the water intrusion, this multiple well. And you can see here, this computational model, and we do a very good match for the water intrusion. Another application is about some people want to say, can you couple EDFM with the DPDK method? Because DPDK still has some useful, because their computational efficiency is very good. So can you do coupling? Yes, we can. And in this field case, we identify 2 different group of fracture based on size. For example, like 10 to 50 meter, there are a lot of small fracture. So we can upscale to single porosity. Actually, in this case, we can upscale to dual porosity model with like a shape factor. And then we use EDFM to model this big fracture. It's more than 50 meter to like 200 meter. This is EDFM grid block. Then we can do very good coupling and to match the production. This shows the visualization of the effect of fracture on the drainage area. Next key technology we extend is about thermal EDFM, because recently several companies talked to us. They want to model geothermal considering this 3D natural fracture. It's very easy. We just put a thermal effect. This we show the one field case study, like one injector to producer, this 3D DFN, and we have some 3D hydraulic fractures. Then we can easily simulate the geothermal development. And also, this case show our EDFM how many fracture you can handle based on current your technology. Actually, we did this test for the unconventional reservoir, including about 400 horizontal well, and including 1 million natural fracture. And for the hydraulic fracture has about more than 800. That's a huge number of the natural fracture and hydraulic fracture. Our EDFM works very well. And the final reservoir model, including about more than 42 million grid block, we run about 32 CPU, is running about 10 times if you model 30 years production. So that tells us our EDFM, we can handle more than 1 million fracture, it's no problem. So next I will show some our ongoing the new EDFM feature developments. Actually, the first one I want to say is about EDFM-AI. Actually, we work on this product more than 5 years. Actually, we work for that for unconventional reservoir to automatic match and calibration your hydraulic natural fracture properties. But now we want to extend this engine to model carbonate reservoir to do automatic match your production with this 3D complex like natural fracture and fault. And here I show some the solution for we did before. Like we can consider different combination of multiple uncertainties, and we can give you the multiple match and also give you the best match. And this show as this red color. And then we can, after the match, and another key thing we can do inversion to calibrate your something fracture property. Like here, we did before for unconventional reservoir, we calibrate the natural fracture length. We give you the P10, P50, P90, and also natural fracture conductivity. So we really believe using EDFM-AI, we can do a better job for the carbonate reservoir automatic match and natural fracture calibration. And the next new feature we want to develop now is about Parallel-GPU-EDFM, because we work on several field projects for the Carbonate reservoir. The natural fracture number almost like full field, almost more than 1 million or several million. So they want to use the EDFM to handle all the natural fracture. But that give us a lot of requirement to speed up of our EDFM preprocessor. So that's the reason we propose this new idea. We use the GPU to do some calculation of our EDFM core function, and then we with multiple core to run our EDFM preprocessor for the several million natural fracture. We do not need to upscale to single porosity or dual porosity. It's much better for the multiple match with a lot of fractures. And another update we want to do is EDFM Petrel plugin, because there is a lot of people, they use Petrel a lot, and then we also love Petrel. So we can develop this Petrel plugin with our SimTech EDGS suite, and then you can all use Petrel platform to couple your geo model and the fracture model, and then run our EDFM. Then we get back your Petrel, and you can use the Petrel to run Eclipse or Intersect and visualization with our Petrel. So finally, I want to summarize my talk. So our EDFM technology provides an innovative solution to bridge the gap between geology, geomechanics, and the reservoir engineer to deal with the 3D fracture complexity. It's really powerful to couple realistic fracture complexity into any reservoir simulator more easily now and more efficiently. So our EDF solution is still improving. We enjoy learning a lot and more from future more field case studies and our collaboration with our partners. Finally, I want to thank our big team to support the EDFM development, and also our industry partner give me a lot of feedback to improve our EDFM much better and much faster. And the next, I think Mauricio will give you a demo, give some feeling about EDFM technology and software.